Am I audible? Hello? Am I audible? Okay, we'll start with mechanical properties of solid. Okay, mechanical properties of solid. So, mechanical properties of solid is something related to the uh, properties of a material or a solid solid of substance, uh, maybe under the influence or under the application of external forces, sometimes pressures. Okay, so the thing is that mechanical properties are nothing but the property inherent by the solid object. Okay, and that is basically visible when it is experiencing some external force or that type of thing. Okay, so first thing we should understand about the deforming force. Deforming force. Deforming force. Name itself suggests the force responsible for deformation, isn't it? So a force which produces a change in configuration of the object. Configuration of the object. Configuration of the object on applying it. On applying it is called a deforming force. So when I discuss about the potential energy, I told you now the configuration. If the configuration is get changed, means if the dimension get changed, okay, of an object, that is actually specially that is known as the deformation. Whether the object is getting stretched, huh? Take an example of wire, steel wire or aluminum wire. If it is stretched or if it is twisted, so basically the general configuration you are changing it. So a force which produces the change in the configuration of the object, or rather I can say a force which is deforming the object, when you are applying that force, that type of force is known as deforming force. Okay, so in this chapter in mechanical properties of solid, will not consider any solid object as a rigid body. Okay, remember very carefully, rigid body in case of rectilinear motion, even in NLM also, what we consider any object to be rigid one. Rigid one means if you apply force on that object, it will not having any deformation, only it will have that velocity, acceleration, all these things. Okay, only the position get changed. But when we say it is non-rigid body, then you understand the concept. When you apply the force, the thing get displaced and there is a possibility that the object get deform also. If you apply certain force which is beyond the permissible limit of that object, therefore it may get some bend, some crack. Okay, so that type of deformation may occur. Okay, so actually no object in this world is actually rigid one. Rigid is a concept that is kind of ideal concept. Okay, so here we are basically dealing with the real properties of a solid, like what happened to it when some external force is applied to it. So first force that we have discussed, that is the deforming force. Deforming force, that is responsible for deformation of the solid. Now we consider another concept or property, I can say, that is known as elasticity. Elasticity. So elasticity, again a property of an object. It is that property of a solid by virtue of which by virtue of which by virtue of which it regains its original configuration. It regain its original configuration after removal of the deforming force. So you have removed the deforming force which is acting upon an object and solid, and when the solid is get deformed under the deforming force, if you just remove that deforming force, it again regain its original configuration, original shape. Therefore this property, so maybe the material having some property na, that is why it basically happens. You have deformed it, again if you just remove the force, it regain its original shape. So therefore this type of property is known as elasticity. This is known as elasticity. Okay, this is known as elasticity. Now elastic limit. Elastic limit. What do you mean by elastic limit? See, elastic limit having a definite definition like elastic limit is the upper limit of, it is the upper limit of deforming force up to which if deforming force is removed, deforming force is removed, the body regain its original form completely. Original configuration completely. That means suppose you are applying a deforming force, suppose 60 Newton. Now suppose for a solid the elastic limit is 100 Newton. So up to 100 Newton you can apply deforming force, there is no problem. That means if you apply deforming force up to 100 Newton and then remove that 100 Newton, then it will again regain its original configuration completely. But if you apply 101, even 100 and 0.5, 100 and 100.05 like that, so then also if the shape get deformed, it will not get back to its original position, original configuration completely. So do you understand? It is the limit of the, it is the, yes, it is the limit or it is the highest value up to which it can basically, if you, it can sustain the external force, and then if you just remove the external force, it will get back to its original position. Now if you just give beyond, little bit beyond this, then it will not get back to its original configuration completely. So that is basically your what I can say, elastic limit. Okay, now what do you mean by perfectly elastic body? Perfectly elastic body, again, it is kind of what I can say, uh, if it says perfectly means that is quite ideal case. Okay, so actually perfectly elastic bodies means those bodies which regain its original configuration, original configuration, original configuration mm, immediately immediately and completely immediately and completely after the removal of deforming force, after the removal of deforming force. What does it means? Perfectly elastic body is that type of solid object or something. If you just remove that deforming force, immediately and completely it will get back to its original configuration, original shape. That is known as perfectly elastic body. So it will not take any time to quickly return to its original shape, and completely, not a single kind of, suppose the length was uh, maybe before elongation it was 1 meter, after elongation it is 1.01 meter, again if you just remove that force, it get back to 1 meter exactly. So therefore this is perfectly elastic body. So if perfectly elastic body exists in this universe, therefore another term should come like perfectly plastic body. Plastic means what? Elastic means it will, if you remove the force, it will get back to its original configuration or shape. Now plastic means if you remove it, then it will basically it will not regain its original configuration. That means it will sustain the deformation. So that deformation must be there. Okay. So elastic bodies are like those, if you just remove the force also, deforming force, it will not get back to its original position. It will have certain amount of deformation within it. So that is basically plastic body. So perfectly plastic body, or I can say bodies. Okay. So that means those bodies which does not regain its original configuration, its original configuration, its original configuration, its original configuration after removal of the deforming force. Okay, this is what actually known as perfectly plastic bodies. Now here comes another concept that is known as stress. That is known as stress. Uh, perfectly elastic body. Perfectly elastic body is actually, we can say, up to certain limit, it can show some perfectly elasticity, but see, it depends on the type of material. Like if I say about the steel, okay, steel are actually elastic. So if you think about like rubber type of thing, rubber is not elastic, correct? Rubber band, that is totally different thing. Rubber band is not a elastic thing. You can see little, because we are applying very little force to it to get the stretch. It is not like that. If you apply a kind of force which you are applying to the steel, the rubber band perhaps, it will be having n number of parts. Okay, so rubber band type of thing is actually what we see in our surroundings. Rubber band, it is the elastic thing. No, those are not elastic. A rubber band, if you have a rubber and if you have a steel, steel is more elastic than a rubber band. It depends on the load, how much load it withstand. Up to what limit load, if you apply to the steel, then it will again regain its original position. Definitely steel is much more elastic. Okay, and rubber band easily you can basically break it by your hand, so it is a plastic thing, not a elastic thing. Okay, so whatever we are seeing in normally, we are applying very little amount of force to basically deforming force to stretch that band. If you apply that much force to at the same type of steel type of rod, it might have some deformation. No deformation. Okay, so quartz is somewhat elastic. Phosphor, bronze, quartz, those are somewhat perfectly elastic, I can say. Phosphor, bronze, phosphor, bronze, phosphor, bronze. This is an alloy type of thing, and another is quartz. Those are perfectly elastic. And this, wax, perfectly plastic. That is wax, paraffin, wax. Okay, those are perfectly plastic bodies. Clear? Hmm? Clear? Now we'll move to the stress strain concept. What is stress and what is strain? Okay. See, stress is not something which is external. Suppose you are applying deforming force to an object, correct? You are applying deforming force to an object, and therefore uh, it is the stress is the internal restoring force per unit area. So what happens when, suppose this is an object, you are applying deforming force to it. So if you basically if you apply both the side, this is kind of tensile force. So this object tends to stretch, isn't it? Tends to stretch. That means it basically tends to deform. Now see, there is an inherent property of that object to resist that deformation. Do you understand? There is an inherent property of that object or the solid to resist that deformation. See, deformation occurred and then it get back to original position, elasticity that is there. But before elasticity, there itself a property of a object to resist its deformation under the deforming force. So, suppose it is getting stretched, na? So there is a constantly a force acting inside that object which resists this deformation, that is this elongation. Do you understand? Do you understand? So that that deforming resisting that deformation, that is a force is there, and that force per unit area, that means the resistive force per unit area is known as stress. So stress is nothing like you are applying this force outside and this force per unit area. It is not like that. Though we can equate this force can be the equal to that resisting force, we can basically apply third law, but it is not like that this force is equal to this force bar area is equal to the stress. Stress is actually, it is the inherent thing. Stress is actually the inherent thing, and it is the, what I can say, it is the internal restoring force per acting per unit area. So we can so it is the internal thing that you must understand. The internal restoring force acting per unit area of a deformed body. Do you understand? Do you understand this concept? So you apply some external force to an object, it tends to deform. So the deformation registered by the internal force itself. When as soon as you apply external force, there is an action of internal force to resist the deformation or to restore it. That means to get back to its original position. So that force per unit area, that force, that internal thing, internal force per unit area is known as the stress. And stress is what actually it is force per unit area. So therefore it is kind of, it is equal to the dimension of the pressure. Pressure is also force per unit area, but it is external force per unit area, and this is internal force per unit area. Clear? Tensile force means the force that is responsible for the object to get stretched. Like this, these two force acting opposite to each other tends to stretch this object, that is tensile force. Okay. Clear? Now, so stress, that is force per unit area, here the restoring force per unit area. So restoring force per unit area, and that should be Newton per meter square, you know. This is the force and this is the area. and the dimension for it m L inverse. Actually m L T to the power minus 2 is for your force, and that divided by this L square. So what it will be? M L inverse T to the power minus 2. Okay, clear? So this is about the stress concept. Okay, now we must understand key stresses are of two types. Stresses are of two types. Two types generally. One is normal stress. Another is tangential stress. Now in normal stress there is two types of stress generally, tensile and compression. Tensile and compression. And this tangential stress is basically uh, the deforming force applied tangentially. Like if I say uh, kind of shear stress. Shear stress. Okay. Volumetric stress is actually that is different. That is actually different thing. That is that is you can say that linear stress. That is along the dimension. Linear stress. You know, superficial stress, that is surface, and then this thing like volumetric stress about the volume. But see, we can classify strain according to the volumetric strain and all these things. Okay, but stress cannot be classified in that way. Okay, that is a force classification in that case. If you are doing like that, strain can be classified as volumetric strain and all these things, but stress are generally normal. One is normal stress, another is tangential stress. And why it is named so? Normal stress means the deforming force is applied normal to the area. In the normal stress, the deforming force applied normal to the area. Normal to the area. Suppose take an example of tensile stress. So here you have an object. I told you the tensile force is in this way. So the deforming force is, you can see this is the cross sectional area. So it makes 90 degree with this cross sectional area. Here also it makes 90 degree with this. So it acts, you know, at a normal to the area, cross sectional area in this case. And what do you mean by then tangential stress? Tangential normal is like that. Tangential means the deforming force applied tangentially. Force applied tangentially. See what I told you about the shear stress. Shear stress is like this. See here, you can see two objects are here, you know, riveted. Riveted means one nut bolt type of thing that have joined these two two plates. Here suppose plate 1 and this is plate 2, and here you have some joining thing that joined or clipped both of them in this way. Suppose a bolt, you see the bolt. Now if you apply force, if the force is applied here in this direction and here in this direction, so what will happen to the bolt over here? You see the bolt is actually joined two plates. Now if you applied force in two plates in this direction opposite to each other, what will happen to that? What will happen to that bolt? This is the bolt. Now bolt is actually cylindrical form. You think about it. Now when some portion of bolt is below portion of the bolt is actually experiencing a force in this direction, above portion is experiencing in this direction. Therefore if I consider, because this is a cylindrical thing, look about this, this is a cylinder. Now if I want to see this cylindrical thing from this view, that is top view, I can see from here. I am seeing this thing from this upside. Okay, so it will be a circular thing. It will be a circular thing. Now you think about the force. One force in this circle act in this direction, another force in this direction. So is it a tangential thing now? Isn't it a tangential thing? Isn't it a tangential thing? See, because the cross sectional area of the bolt is circle only. See, very clearly, it is a very unique concept and it is a fundamental concept. Most of the students get confused about this. When I say this, it is when I say it is a kind of this thing, normal force, that is normal stress, it is very easy to understand. Like it is there and this is the surface, so it makes 90 degree with it. But when I say tangential stress, then you need to consider like this. Is shear stress. Shear stress means two plates are bolted together. A bolt is applied over here. Okay, a bolt. Do you understand bolt? A cylindrical type of thing, na? So bolt is basically, that means here you have a plate, here you have a plate, both of plate are in this way, and you made a hole and then you put a bolt inside this thing. So you have jointed both of them. Okay, now if this below plate is experiencing force in this direction and this above plate is experiencing force in this direction, then what will happen? What is the fate of this bolt? How the bolt get experiencing these forces? What you should think then, don't look from this side, you should look from the above side. Above side means you should, if you see a cylinder from the top side, you will see a circle. Now in this circle you see one force in this direction, another force in this direction. So both of them are actually tangential to each other. That means this is the surface area, but the forces acting on it is tangent to that surface area. Tangential, yes, that is what I am explaining. And this is basically your shear stress. This is actually the shear stress. The shear stress often can be experienced by this type of fastening devices. Fastening devices means these bolts and then screws and then rivets, all these things. Okay, clear? Clear or not clear? Reply, I need reply. Okay, now moving to the next concept, that is strain. That Ognivo actually Ognivo is actually telling about volumetric stress, not stress. Actually we will consider strain in that case. Okay, and you are saying the volumetric stress type of thing, now that is kind of tangential thing if you consider that thing. Okay, because shear is kind of volumetric stress. Okay, now but in normally for strain we will be saying all these things. Okay, strain. strain. Strain is nothing but change in dimension to the original dimension. Change in configuration to the original configuration. Change in configuration, it is a ratio. Change in configuration to the original configuration. Original configuration. That is actually strain. And strain is somewhat, it is denoted by this epsilon type of thing, okay, and this is epsilon, okay. Change in configuration by original configuration. Let me tell you very clearly, it is nothing but, suppose if you have a rod of L length and you are applying force both the side, so tension force, that means this thing it gets increased. So suppose the enlarged or the elongated object having length L plus delta L. So what is the change? Delta L is the change. So delta L by the original length is the strain in this case. Delta L by original this L is the strain in this case. And here we can say it is the linear strain. It is the linear strain. So strain is what? Strain is actually the change by the original. The change by the original. That means when you applied the deforming force, definitely the deformation will occur. So the deformation, the amount of deformation by the original, that is actually the strain. Okay. And if the strain in happening in one dimension, either in x, y, z, so that will be linear. If two dimension, maybe in a plane it can happen, then you can say it is kind of area wise strain. If in volume, then it is volumetric strain, okay. And also shear strain is also there. So generally we will say linear strain, volumetric strain and shear strain. These three strain are main important strains, okay. So see, for volume it is quite easy. If you have a cube like this, so if the original volume is V, if it gets changed to V plus delta V, so this is the change in volume. So delta V by V is the volumetric strain in this case. So you can say it is epsilon, here V, that means it is volumetric strain. That is change in volume by original volume. Simple concept. Don't take it in so much complex concept. You have an object, you apply the deforming force, you get the deformation. So the deformation by the original dimension, that is the strain. Okay. Clear about it? And it doesn't have any dimension. Why? This dimensionless quantity. Because it is a ratio of the same type of thing, na? Same type of parameter, na? Correct? Yes. Now, here we'll see what do you mean by shear strain. Shearing strain, I can say. Shearing strain, that is actually kind of thing that can be explained in this way. Let me explain it in a different diagram. Suppose if you have a cuboid, this type of cuboid box, okay, cuboid type of box, so I am showing you in 2D. It is a 3D concept, but I am showing you 2D. That is, I am showing you the side view. Side view, if you look at an object from the side, this is the side view. Okay. Suppose this is the dimension M, N, O, P. These are the fixed 4 points of that. Because if you see a cuboid from the side, you will see a rectangle. So that is what you can see over here. Now, if I apply force on this side, what will happen to it? It get deformed. It get deformed. So it get deformed. See, it get deformed in this way. This P comes to this point P dash. I am showing little bit more deformation. Rather, it could be very small deformation, but I am showing you just to make you understand this concept. This P comes to this P dash, that means it get deformed, and this O comes to this O dash. So now the shape of the rectangle becomes like this deformed shape. Yes or no? So what we'll do? We'll take this angle. So originally this was the dimension, and it get deformed in this way. So this angle I want to get. Suppose this angle is phi, and we can get that thing because if I consider this phi, so I can take tan phi is equal to what is tan phi? This is the acute angle phi. So opposite P dash is opposite P dash by adjacent PM. That is the tan phi. So phi is equal to tan inverse of P dash by PM. That means this is what you can say. This phi is nothing but angular displacement of the plane. Angular displacement of the plane. Now you see this tan phi is what? This P dash by PM. So this tan phi can be named as the shear strain, because P dash gives you the angular displacement thing, and this PM is what? The fixed plane. So the displaced plane concept is given by P dash, and the PM, this is the fixed plane. So P dash by PM, that is nothing but tan phi. That is, you can say this is a shearing strain. And this phi is actually tan inverse of P dash by PM. So tell me, is it clear? Is it clear up to this? Everyone must reply. This, this PM displays to MP dash, and OM displays to, sorry, ON displays to, or NO displays to NO dash. Correct? So that angle, the sidewise angle, that phi, that is the shear strain, you can say. So shear strain, shearing strain, having a definition: angular displacement of the plane perpendicular to the fixed surface. To the fixed surface. Okay. Now here comes a law, a very well celebrated law in this material, mechanical properties of the matter or solids, that is known as Hooke's law, and it is kind of a law which gives you relation between stress and strain, and also gives you a new concept of modulus of elasticity. So what this Hooke's law basically says, Hooke's law having a statement. Law. It states that within the limit of elasticity, within the limit of elasticity, within the limit of elasticity, the stress is proportional to the strain. The stress is proportional to the strain. You know the limit of elasticity. Already we have discussed elastic limit. So up to that limit of elasticity, the stress is proportional to strain. So stress is often denoted by sigma. This is proportional to strain. Strain is epsilon. So what I can say, stress is equal to, if I bring equal, so I must bring a proportionality constant, and that has to be E here, capital E into epsilon. Therefore capital E is equal to sigma by epsilon. So capital E is here the proportionality constant. Here it is known as modulus of elasticity. Modulus of elasticity. Modulus of elasticity. And as you can see, capital E, modulus of elasticity, is equal to stress by strain. Strain doesn't have any unit because it is a ratio. Stress having the unit solely. So the unit of stress is equal to the unit of modulus of elasticity. So whatever the unit of stress, that is the unit of modulus of elasticity. Generally the unit of pressure, I can say, because stress is also having the same unit as pressure. Clear? Up to this it is clear. Now this modulus of elasticity is not the sole modulus that is there in this chapter. We have different modulus also. The types of, so there are generally three types of modulus of elasticity. Types of modulus of elasticity. First type, that Young's modulus. Young's modulus of elasticity. Young's modulus of elasticity. That is nothing but denoted by Y, capital Y, and that is normal stress. Normal stress, you know the normal stress, either tensile or compression. Normal stress divided by longitudinal strain, that is linear strain. Longitudinal strain. So the ratio of these two fellow is known as this Young modulus. So Young modulus Y is nothing but normal stress can be written as this force by unit area, isn't it? Yeah. That is there na, force by unit area, that means restoring force by unit area. And longitudinal strain is delta L by L if I consider. So if I rearrange them, that will be F, so A will go down, isn't it? So what you will be having, this FL by A into delta L, isn't it? Okay. And therefore, if you want to get a relation between these two things, it will be FL by A into delta L, or from here if you want to get delta L will be FL by YA. Delta L is the deformation, linear deformation in this case. This is the about the Young modulus of elasticity. Clear or not clear? Clear or not clear? Okay. Okay. Now the second modulus of elasticity. This is the first modulus of elasticity. Why? Why is Young modulus? Young modulus of elasticity. I told you na. This is the Young modulus of elasticity. This is why. Okay. Now the second modulus of elasticity. Second modulus of elasticity is actually bulk. Bulk modulus of elasticity. What do you mean by bulk modulus of elasticity? Bulk modulus means it is the ratio of normal stress to the volumetric strain. It is denoted by K, that is normal stress by volumetric strain. So normal stress, you know, it is F by A, and volumetric strain is delta V by V. So it will be F into V by A into delta V, that is the K. Okay. And therefore I can say delta V can also be written as FV by KA. Correct? Clear? Okay. Clear? Now see one concept, that is whether it is your Young modulus or it is bulk modulus, all of them having a common type of unit, because you can see the unit of the stress is actually basically unit of this modulus. So it is Newton per meter square, and the mostly used things are actually megapascal we are using, kilopascal we are using. Okay, and definitely the Newton per meter square also we are using. Okay, because Newton per meter square is nothing but this Pascal only. Okay, but generally we will be using megapascal, that is 10 to the power 6, or kilopascal 10 to the power 3. Clear? And the dimension of this modulus are actually the dimension of the stress. ml inverse t to the power minus 2. Correct? Now we'll consider the third one. Third one is modulus of rigidity. Rigidity modulus. It is saying rigidity modulus. Modulus of rigidity. Rigidity modulus. Modulus of rigidity. Sometimes denoted by eta, or maybe you can see in some books G, or sometimes C also. Okay, so various notations are used, so don't get confused. All of them are rigidity modulus only. Okay, and this is eta. So rigidity modulus is nothing but it is the ratio of tangential stress to the shearing strain. This is the only modulus that deal with this shear and this tangential stress. Okay, so eta is equal to tangential stress by shearing strain. Shearing strain, I have described you what is shearing strain. Okay, and also it has that the same thing, like uh, the same concept you can use over here, like uh, the unit Newton per meter square here also, or Pascal or kilopascal, like that. And the dimension of m L inverse t to the power minus 2. Okay, now we do have one concept that is known as compressibility. Compressibility. Compressibility is actually reciprocal of the bulk modulus of elasticity. It is denoted by C, and it is 1 by K, bulk modulus of elasticity. So definitely if K is Newton per meter square, so it will be Newton inverse meter square. The compressibility unit is Newton inverse a meter square. Okay, but you remember, Sutopa, you have a wrong conception. Now you make it clear. Steel is more elastic than rubber, and solids are more elastic, and gases are least elastic. Gases are least elastic. Okay, and also some point to note, like modulus of rigidity is 0 for liquid. For liquids, modulus of rigidity is 0. Okay, so Young modulus and modulus of rigidity is possessed by solids only. Okay, clear up to this? Now moving to the next thing, that is uh, here are something like uh, some concept like breaking stress, breaking stress, breaking stress, breaking stress. So breaking stress is the, I can say it is the minimum value of stress required to break a material or make a break a wire. Okay, so so what you can see, like breaking stress is actually the minimum, the minimum value of stress required to break a material, required to break a material. Okay, so here comes one concept, SOF, or I can say safety of the safety factor, or I can say it is factor of safety, that is FOS. So factor of safety. So it is very important concept to mechanical design and all these concepts. So why it is so important? Because factor of safety is nothing but it is the ratio of this breaking stress. Breaking stress, by now you know what is breaking stress. Breaking stress divided by working stress. Working stress. Okay. So therefore, breaking stress is the minimum value of stress required to break the material, and working stress, the stress basically uh, that is stress you are working with. Okay, the amount of stress you are working with. So so the ratio is often is very important parameter to design a component. Okay, so also this factor of safety, this factor of safety have a different what I can say, different type of concept that is there, like designing. If you design, you want to design a shaft or that type of thing, so factor of safety can also have a definite thing, like I can say it is a ratio of maximum or the ultimate stress by the permissible stress. Okay, ultimate means the breaking stress, ultimate stress by the permissible stress. Now you may ask me, so what is this working stress, or you are saying permissible stress? When you are designing a material, now designing means when you are making a material and you are doing all the necessary calculations. So we should calculate that uh, like how much stress that structure it's safely it can withstand. That is the working stress or the permissible stress. and the breaking stress means the structure will failure in that case. Okay, it will be failure. It basically fail, the structure fails. Okay, so therefore it is much more important parameter in this case, much more important parameter in this specific chapter where we are basically studying the mechanical properties of solids. Okay, clear? Clear about this? So factor of safety is also unitless, correct? It is a safety factor. It is actually having the numerical value. Okay. Now we do have some material classification. Some materials are known as ductile material. Ductile material. And some are brittle material. So what do you mean by ductile material? If you consider ductile material, what do you mean by this ductile material? So ductile material means the material which show large plastic range beyond elastic limit. Okay, the material which show materials which show large plastic range beyond elastic limit are called ductile material. Example, like copper, aluminium, iron, silver. Okay, so what does it means? Just think it very carefully. If you have a material, let's suppose a metal, huh? Aluminium, small aluminium rod. So that metal has a specific elastic limit. That means the elastic limit up to which the Hooke's law will be, Hooke's law is not violated, up to which the Hooke's law is maintained. Okay, but beyond that elastic limit, what will happen? If you deform it, it will not get back to its original position, isn't it? Original configuration after removal of the deforming force. That means it will have some permanent deformation, and that is known as the plastic range. But the thing is that by the definition you can see the material which show large plastic range. That means beyond elastic limit you apply, you get the deformation, but the material will not fail. It will deform, but it will withstand. It will deform, but it will withstand. Suppose you are stretching a wire, it get deformed. Okay, it is not getting back to its final position. It lost its elasticity, but still it is plastic. Plastic means what? That means you are deforming, it is not breaking. It becomes very thin, no problem, but still it is there. So that type of material is ductile material. That means If you try to make a wire out of that material, you can make it very easily, because you need to just pull the material, pull it by the hydraulic force and all this force. You can get an n number, any length of wire out of it. That is why most of the wires are made up of copper, aluminium, and all these things. Okay, so you can give them any shape very easily. They can withstand the permanent deformation. That is the plastic thing. Yes, gold is also. Yes, yes, but very precious. That is why I have not mentioned it over here. Definitely it is ductile. So you can have this aluminium foil, gold foil, all these things, na? Okay. So that means beyond the elastic limit, if you want to basically deform it, it will have a large plastic range. That means it will sustain the deformation, but it will not fail. That is the nature of the ductile material. That means you can form very thin sheet out of it, or you can make it, get the wires out of it. Actually, making thin sheet out of any kind of material, that is known as malleability, not ductility. But ductile materials are also malleable. Okay. So ductile material, the property of the ductile materials is known as ductility. That means you basically make it long wires and all these things, stretch it. Okay. And another material is brittle material. Brittle material. Brittle. Brittle means, you can understand, those are hard, but they can break very easily. They doesn't have that much of plastic range, like cast iron. Brittle materials. Brittle materials are the materials which show very small plastic range, almost negligible plastic range. That means up to a certain limit, you apply force, it will break very easily, like cast iron. So the definition for this, the material which show very small plastic range, like cast iron, glass, ceramics. Okay, those are like this. So still they are actually having plastic range, but very small compared to the ductile material. Clear? Very small plastic range. Okay. Now the elastomer. That is what known as, the rubber and all these things. Elastomer. That means elastomer doesn't have any plastic range. Elastomers, easily, if you just apply force, it will break. That's all. Elastomers have no plastic range. Okay. So that means here, what is the definition of it? The materials for which strain is the produced strain for which produced strain is much larger than the stress applied. Much larger than the stress applied. Within the limit of elasticity. Within the limit of elasticity are called elastomers. Are called elastomers. Okay. Now we do have one concept that is about elastic potential energy in a stretched wire. Just look at this concept very carefully. Elastic potential energy in a stretched wire. In a stretched wire. So when I say potential energy, so first you need to understand there must be some work done to stretch a wire, and that work done basically stored in the form of potential energy inside the wire. You have done some amount of work, and that work is actually stored as a potential energy, isn't it? Acha, Bunny is asking for this, or which one? This one. Bunny, are you asking for this brittle material? This slide only. This one you are asking for. Is it done? Okay. Now actually I was asking about this thing, like when you are stretch a wire, definitely you have to do some amount of work. Okay, and that work, the work done is actually stored as potential energy inside the wire. That is the basic concept. Examples of elastomer. OEC is asking for examples of elastomer. Elastomers like this thing, rubber type of thing, rubber. Okay. Okay. So what I am saying that whenever you are stretching a wire, so the work done, so actually work done is actually average force into increasing length, and that is the potential energy. So potential energy, that is actually U. Okay, that is equal to average force into increase in length. Increase length. Okay. So why we say average force? Because see, normal, if this is the initial condition of the wire, you are still actually you have not applied the total force. So initially the force was 0. Now when you stretch it, the force is maximum F. So average force is F plus 0 by 2, that is F by 2. So F by 2 into the change in length, suppose delta L. So I can say half into F into delta L is the potential energy in this case. Now can I write it little bit different form, like uh, this thing can also be written in this way, like this f into delta L is there na, f into delta L is there. So you see um, f into delta L, if you take that concept, f into delta L. So this thing we can change to, like we know one concept like this, if we want to consider volume of the wire, okay, we can write it half into stress, that is sigma, into strain epsilon, into volume of the wire, if we consider as a whole, if you consider as a whole, because now this is for total volume. Now if I want to say elastic potential energy per unit volume, elastic potential energy per unit volume, per unit volume. So what you will be having then, this V get cancelled, so we'll be having half into this sigma into epsilon. Now if you see this sigma, sigma is F by A in this case, and epsilon, epsilon is actually delta L by L, okay. So therefore this thing, like we can do in this way, like if we write down this concept half into sigma into epsilon in terms of uh, Young modulus, how do you can write this thing in terms of Young modulus? See, because we know this thing, like Young modulus is equal to, you can say, if this is there, now I am writing here half into sigma. Young modulus is what? Sigma divided by epsilon. Now I am doing a simple trick. See, divided by epsilon, so I made this epsilon square. I can do this thing now, because I have divided an epsilon, so I made it epsilon square, because I need to keep this quantity na. So it becomes half into Young modulus is y into epsilon, that is strain square, okay. Now which is quite similar to the potential energy in a stretched spring, because it is potential energy in a stretched wire, half into y into that epsilon square, or I can say half into Young modulus into strain square. That is quite similar to what we have seen elastic potential energy of a stretched spring. For a stretched spring it was half into k into x square, isn't it? Whereas k was the force constant of spring and x was the change in length. Yes or no? बताओ, tell me. Is this clear? No one is actually replying me that in that case. See, no one asked me this question, sir. You have written U potential energy half into F into delta L. That is the work done. Average force into. Then how you can arrive this in this way? Huh? Because see, this is when you are considering for a volume, simply you can consider in this way. See, if you write half into F into delta L, now this is for unit volume. Now for the total volume, can I write into V? Yes or no? Now this same volume, if I divide with this, just look at the concept what I am doing. Okay. Now half into F into delta L, volume I can write area into L, length, 2D into 1D, it is volume, and that is again this thing is there. So F by A is what? It is that sigma. Del L by L is what? It is this epsilon. That is why it is getting in this way, half into sigma into epsilon into V. That is stored, that is, potential energy stored in the volume V. That is how I arrived in this, that condition. Do you understand now? Clear? Now I am moving to thermal stress. Thermal stress. Thermal stress. Thermal stress is actually when temperature of a rod or that type of thing is changed, then generally that object is under the thermal stress. How? Suppose you have a rod that is having two fixed ends. See, this is a rod in between them, and these two ends are fixed. Now if you increase the temperature of this rod, definitely this rod wants to expand. If it is a metal type of thing. Now but the end you have constricted, now you have constrained over this thing. So therefore this rod will experience the thermal stress in this x-axis, if you consider this as x-axis, and this thermal stress is denoted by this if I consider key this length is L, so L and then alpha, coefficient of thermal expansion, and delta theta. Delta theta is nothing but it is not an angle, okay, it is the temperature difference. You can say delta T also. Some books have written delta theta, some books can actually written L alpha into delta T. That is also correct. Both of them are correct. Actually delta theta or delta T, that is the temperature difference. Okay. Now in terms of bulk modulus also we have it. In terms of bulk modulus also we have it. In terms of Young modulus we have it. In terms of bulk modulus also we have the thermal stress. We can write this thing, the thermal stress, in linear this what I can say, linear expansion case. We can write it y, then alpha, then del T. It is for the linear expansion. And this is actually the thermal loading, this L into this thing now, because it is the thermal load. Now load is nothing but force. Then if you have this force, but you need the thermal stress. Stress means per unit area. That time you will be having Y then alpha into delta T. Now if they ask you thermal force or thermal load, that is L alpha delta theta or delta T. Both of them are correct. But if they ask you thermal stress, it is Y alpha delta T. Y is, you know, the Young modulus. It is for the linear expansion. Now what for the thermal stress for, you know, when you have this bulk expansion, you have bulk modulus of elasticity. That means volumetric expansion. Then it should be thermal stress in the volumetric expansion should be K and then this thing K gamma into delta theta. K is bulk modulus, you know. Gamma is coefficient of cubical expansion, coefficient of cubical expansion, volume wise, na? And delta theta is nothing but change in temperature. Correct? Bolo, is it okay or not? Up to this, it is clear or not? Clear? Now here we do one relation, we do have one relation like interatomic force constant. Interatomic force constant. This is an important small formula. Interatomic force constant. This is denoted by R naught. This is interatomic force constant. That is equal to K by Y. K by Y. Okay. Interatomic force constant. Now the Poisson ratio. Poisson ratio. Poisson's ratio. Poisson's ratio. Poisson's ratio means it is the ratio between the lateral strain to the longitudinal strain. So Poisson ratio is nothing but it is the, so it can be denoted by mu. Mu is equal to lateral strain by longitudinal strain. So lateral strain by longitudinal strain. And always you should remember the theoretical value of Poisson ratio. Theoretical value of Poisson's ratio will be lie between -1 to 0.5. That is theoretical value. But practical value, that is from 0 to 0.5. This is important. Theoretical value -1 to 0.5, practical 0 to 0.5. Now there is a relation between this y, that is Young modulus, then actually there are 4 relations, then bulk modulus, then modulus of rigidity, and this mu means Poisson ratio. So actually 4 relations are there. Relation 1, y is equal to 3k, you need to by heart this, 3k into 1 minus 2 mu is the first relation, but these are very important. Number 2, y is equal to 2 eta 1 plus mu is number 2, and then number 3, sigma is equal to mu is equal to 3k minus 2 eta divided by 2 eta plus 6k. This is number 3, equation number 3. And equation number 4 is this, you can write y is equal to yes, we can do in this way, we can combine both of them. Actually we can combine it and we can get this in this way, 9 by y is equal to 1 by k plus 3 by eta. Now you can basically make it in this way, k eta, and this is eta plus 3k, and therefore this because here it is 9 by y, so this you can multiply over there. So 9 into k into eta divided by eta plus 3k is equal to y. This is also another relation. These are all important relations for all these Poisson ratios and all these things. And this stress strain curve, this Hooke's law, there is an important stress strain curve that has to be thoroughly studied in this part. The stress in y axis, strain in x axis. Now you see, if I start from this origin, this I name it as 0 to a will be something, and then from a to b will be something. I'll be naming all this thing, and then b to c, this is b to c is something, then like this, this D, I need to, yes, this is D, and then finally E. Now what is this O to A? This is known as proportionality limit. Proportional limit. That is, this Hooke's law is actually up to this. And then B point. B point is upper yield point. Upper yield stress point. That means up to B it will be kind of, elastic plastic nature, but after C, you see the C is the lower yield stress point. Lower yield stress point. D is the ultimate stress point. That means after beyond D, if you go, means it will break. Ultimate stress point. Ultimate stress point. And E is the fracture, that final breaking, fracture. So these are all important points. So you see, from if you grow from O to A, that is linear in this region, Hooke's law and proportional limit law, that is Hooke's proportional limit law, is obeyed. Now A to B, it is like stress and strain are not in proportional. Still body regain its original dimension once the load is moved, but it is not getting the exact original dimension. Okay, so A to B is still elasticity is there. At point B, the curve is actually yield point or elastic, I can say it is the elastic limit. It is known as upper yield stress point. Okay, and this B, beyond B, the reason is basically plastic deformation. Beyond B, the B to C is the plastic deformation. Now C is the lower yield stress point. Now you see the point D, the curve shows the tensile strength of the material. Beyond this point D, if you add extra force, anytime the material can break, and even you see in E point the material get fracture. So this is how you can have the proper picture of any kind of, and especially this is for ductile material. For brittle material, you see this much of, because here you get B to D, this plastic region, this much of plastic region will not be there in case of brittle material. Brittle material having low plastic region, but it is for ductile material, so you can see the more plastic region and all these things. So it takes time to break. Correct? So this is the total picture of the stress strain curve. This is also important. Clear? Clear? Okay, so I am wrapping this class here. The fluid thing, that is the surface tension part, because this is the solid part I have done, that will be done within some 2 or 3 days. I'll be intimating that class. Okay, like surface tension and all these things, fluid property, capillarity and all these things. Okay, and this is the base, all these parts, and the numerical part I'll be sending you to do, because the formulas I have discussed. Now you need to practice those numericals. Okay, clear? I'll be informing you within some 2 or 3 days. Okay, that is actually fluid. This is the solid part is done. That part is fluid. So that will take another one class to do that thing. Okay.